so much, and it's a pleasure to be here in London. I love this city, I must say. It's a wonderful city. I have family here, living here. I'm coming from Brussels. So yesterday I was flying in from Brussels, and I came to Heathrow, and I thought, no, let's take some time to go through London. I want to see what's going on in this lovely city. So instead of taking the taxi immediately here, I took some public transport. I was walking a bit just to see, get a feeling what's going on in London these days. And as usually, there's a lot of things going on in London. But what strikes me is that there's a lot of traffic issues in London these days. There seems to be a lot of roadworks going on. I guess we have the same in Brussels, by the way. So could we imagine, just as a thought experiment, think about it, could you imagine London without the traffic police? Just think about it. What would that mean? What would be the solution in order to help the police force, which may have some more pressing needs these days than trafficking or traffic control? Well, maybe one solution to that could be this: the robotic traffic police. Actually, that's a very intuitive solution for us. And why is that? This is what we call a self-confined solution. It's all in one package. And we human beings, we are self-confined. We're all in one package. So we tend to think self-confined. When we come up with solutions, it's usually something in a package. Because this will probably solve the problem in a way very similar to the way we would solve the problem. But with innovation over the last 100 years, we don't need self-confinement anymore. I mean, what we have done is we have managed to distribute electricity over way further than 1 meter. And with the internet, we can distribute information much, much further. So if we leave this idea of thinking self-confined, maybe there are better solutions. So let's try again. What would be a better solution than the robotic traffic police? Well, maybe something like this. Maybe you could imagine London with a lot of self-flying drones hovering over the city and monitoring the traffic. And these drones can communicate with cars. Some of them may be self-driving to some extent, and with other sensors and nodes in the environment, with satellites, with human beings, to form a system around this which can solve the problem. The benefits of such a system is that it's much more agile and it can adapt to different types of situations. For example, these drones, when they're not monitoring the traffic, maybe they can deliver your groceries, or they can do some other tasks. And the same with self-driving cars, which can act as emergency vehicles in case of an accident. But when there's no accident, maybe they can deliver people. So this type of system is much more flexible. But there are a few problems that we need to solve in order to realize these systems, and that's actually what I would like to talk about today. There are fundamentally, we believe from an iMinds perspective, 3 different research challenges we need to attack. And that's basically what I would like to discuss. The first one is about connectivity. So we need, for this system to work, everything has to be connected. But not only connected, it has to be connected in a way that it always works. We call it deterministic communication. For example, there are people in these cars. If the traffic is not going through, someone may get killed. This is a matter of life. This is a mission-critical situation. So we cannot accept that the traffic doesn't work. So how do we connect all these things in a deterministic way? Secondly, how do we establish trust in between all these entities? So trust is a very important word, and it's more than security. And if you think about the situation, there are a lot of different things: drones, cars, sensors, satellites, and they're all establishing all this communication and entities in an ad hoc fashion. They don't know each other to begin with. So how can you bring in new devices and establish trust in this system? If you think that one of these entities is compromised, start to send out the wrong information, the system can be compromised, and actually we can end up again in a very dangerous situation. Bear in mind again that this is a mission critical system, people in the cars, someone may get killed. And finally, how do we distribute the intelligence? It's clear that there must be somehow a certain degree of decision making here. And as you know, these days we believe a lot of this decision making will be helped out by different types of machine learning, artificial intelligence type of algorithms. But the question is, where do we put the intelligence? And what we should remember is that a lot of these devices are rather simple. They are what we call constrained. They don't have large memories. They don't have large processing capacities. Many of them are actually battery powered. So where do we put the intelligence? Do we put it in the cloud? Do we put it on the sensor node or somewhere in between, or do we distribute it? And that's the last topic I would like to cover a bit, what we do in iMinds with this. But let's start with connectivity. And one of the most difficult connectivity problems you can imagine is actually a music festival. So what you see here is some pictures from one of the biggest techno music festivals in Europe. It's taking place in Belgium every year, actually next week. It's called Tomorrowland. And at Tomorrowland, we have 80,000 people coming. So they have 80,000 bracelets. They have 80,000 mobile phones. We have about 1,000 wireless routers at Tomorrowland. And there's massive, massive interference. And we love it, because from a research point of view, this is perfect. This is the testing ground to do the most advanced wireless networking studies you can imagine. And more than that, you know what Tomorrowland looks like today, the week before? It looks like this. There is no infrastructure there. So we have to build it up all from scratch. There is nothing. So this is perfect. And so iMinds have been working together with Tomorrowland for a number of years. And I cannot tell you what we're going to do next week. You have to go there. I can promise you there is some magic. But this is what we did last year. So we created this bracelet together with them. And the bracelet, they said, okay, the bracelet is, of course, to get into Tomorrowland and to do some payments. But they had one additional feature they wanted to try out. And that was to be able to synchronize the light-emitting diode on the bracelet with the music. And again, there are 80,000 bracelets. It's all free-running, very simple devices, free-running clocks. How do you do that? Check it out. So that was just a little short video clip from Tomorrowland last year. I can tell you this year, we are going to show some more advanced, magic and fireworks at Tomorrowland using our technologies. But anyway, this is a super interesting project and also tells you a bit how we work in iMinds together with industry in order to realize this. So what we did was actually to develop a specific protocol in order to synchronize this. It's a proprietary protocol for this specific application, which is latency optimized, because the point here is that we need to synchronize 80,000 devices on this type of infrastructure. So to give you another example, so this was Tomorrowland. It takes place south of Antwerp, so we're coming from Belgium. A bit more to the north, we have Antwerp itself, and there iMinds is now building one of the largest smart cities projects in Europe. We call it City of Things. And City of Things will be a mixture of a technical test bed and also a living lab for Internet of Things applications. But before there was City of Things, there was something else in Antwerp, and that was the City of Strawberries. So strawberries are interesting fruits. Actually, it's not a berry, by the way, it's a fruit, for those who are interested in this type of ecological aspects, contrary to what the name suggests. So strawberries are actually, of course, they're very tasty, and they're actually rather cost optimized. They're quite cheap. I guess you can get 10 strawberries for £1 or sterling or something, I would guess. They have their own internal battery. They're solar powered, you don't need to connect the strawberries. But there's something else about strawberries. And strawberries are actually excellent biometric sensors. So if you have a strawberry and you grow it over time, air pollutants will accumulate not on the berry itself, but on the leaves. And that can be used to check air quality. And this is what they did in Antwerp. There was a project called basin, that's Antwerp dialect, where they put around 1,000 strawberry plants in Antwerp to check the quality of the air in Antwerp. So volunteers in Antwerp, they were growing strawberries for 2 months, and then the strawberries were taken back and analyzed in the laboratory. And by doing so, they could get to maps that looks like this. So here you see a number of dots in different colors, indicating the level of air pollution in Antwerp. And if you look at this map, I think there's no obvious trends, actually. If you look at this, it looks like a rather scattered picture. And it is a rather scattered picture. I mean, contrary to what we thought, it's not obviously so that living close to the ring road in Antwerp is more harmful or has more air pollution than living in the center of Antwerp, for example. If you start to scrutinize the data a little more, you will see that living further up in a building is better than living close to the street. The garden is somewhat better than the street, rather intuitive results. But still, this raised a number of questions. It was an interesting study, but it raised a number of questions about the air quality in Antwerp. So we said, maybe we can do better. Let's try another approach. Let's try the following. Instead of using strawberries, let's use the postcards. In Belgium, we have something called B-Post, who delivers the post. So they're anyway going around in Antwerp all the time. If we can put sensor nodes on these cars and measure things like air pollution, but more than air pollution, we can measure humidity, carbon dioxide, we can measure temperature, we can measure everything, and we can even deliver the post. So it's really a multi-purpose system. Such a system would be probably better. So how would it be better? Well, this, just to give you an example, this is an example from a few weeks ago where you see actually the track of 2 cars running or driving around in Antwerp, delivering the post, and where you can see the degree of certain air pollutants in terms of the color, and you see the width of the line which indicates the carbon dioxide level. So it's just to illustrate that these are results we get in real time, all the time these days. By comparing strawberries with our solution, well, the point about strawberries is that it's actually quite good. You know, it's eco-friendly, it's power efficient, and it's low cost and so forth. We want to preserve these topics or these properties. But what we wanted to add to the mix was real time to begin with. Because you remember it took 2 months to accumulate the results on the strawberries. You know, if it takes 2 months, it's very difficult to take a decision. We want millisecond information. So in case there is a problem with air pollution in Antwerp, we can reroute the traffic. We also wanted some degree of smartness so that we can take decisions locally. And I'm sorry to say, but strawberries are not very clever. They have a lot of properties, but they are not very smart. We wanted something a bit, speaking about the previous speaker, we wanted something which was based on open standards, so more developers can use it as well. Something that is multi-purpose, meaning that we can not only check air pollution, but also temperature, humidity, and so forth. And we wanted something that was secure. And strawberries are not secure. The data you have on your strawberry is completely unsecure. Anyone who steals your strawberry will get your data. So how can we make it completely secure? That brings me to the next topic about trust. So trust is an interesting topic, I think. Trust is an interesting word. When I came here yesterday, well, let me maybe say the first thing is I trust you to begin with. I mean, I trust that no one here in the audience has a gun and will kill me. That's a trust in you. Of course, I don't know you, so how can I trust you? But yeah, it's the way we built our society and our system. I trust you, although you may disagree with me, you will not kill me. That's a trust in a system. When I was coming here, when I was flying yesterday, I trusted that the pilot could fly the plane. But did I trust the pilot? Really? That's not possible. I don't know the pilot. I didn't even see the pilot. So I couldn't possibly trust the pilot. I trusted the system that trained the pilot. I trusted the system that maintained the plane. I trusted the system around how they direct the traffic, air traffic control and so forth. I trusted the system. So it's a question about trust in systems. And when the trust disappears in systems, of course we have a problem. And the point about trust is it takes years to build it up, but it takes only a few minutes to ruin it. I think everyone who has followed the debate about the Tesla now knows the problem. This is a problem also for IT systems. So it's the same problem. It's a question about trust in systems, and the lack of trust is really harmful. So what are we doing in iMinds when it comes to trust? Yeah, we have a long history in this. Actually, to be a little more technical, for those who know the advanced encryption standard, that's the most widely deployed encryption standard in the world. It's the only encryption standard that's ever been approved, the only public encryption standard that's ever been approved by NSA. So you all use it every day, and we invented it. So this is something we did a few years back. The advanced encryption standard was invented in Belgium by researchers within iMinds. So you really have iMinds inside your devices. So AES is fantastic, it's almost unbreakable as an encryption standard. But what we're doing these days is to see how can we take this knowledge to apply it in the cloud, because AES was not designed for cloud. We didn't think about cloud in those days. And how can we apply AES and other encryption standards on small devices? Because AES was never actually built to be power efficient. It's rather power efficient, I have to say, but wasn't built. This was constructed before the age of Internet of Things. So just to give you a few of the keywords these days, one of the hot topics in encryption these days in cloud is, I forgot this one. If you want to read more about this, it's in the fascinating story, by the way. Go to the Wall Street Journal, read this story of how Belgium actually became the powerhouse of encryption in Europe. It's an interesting paper. But anyway, what's interesting these days is how can we apply encryption in the cloud, for example. And one of the topics, I'm not sure if you heard it before, homomorphic encryption. If you haven't heard it, remember it. It's one of those terms that will come back. The point about homomorphic encryption is basically that the cloud is always encrypted. Today, if you make a search on Google or something else, is he awake there? No? Actually, what happens is that you decrypt, because you can't search on encrypted data. So it may be encrypted, but when you do the query, you have to decrypt. And then you search on plain text, and then you encrypt again. So that's a vulnerability. We talk about what we call the attack surface. Here we have a problem because there is a weakness. So imagine that you could search on encrypted data. So instead of decrypting the data is always encrypted. And that's what we call homomorphic encryption. And it means that the data will always be encrypted. And this is one of those breakthrough technologies we're working on. It's mathematically terribly complex, but it will have huge consequences. On the other side of the spectrum is how do we apply encryption on small devices? So we have small devices for Internet of Things, sensor nodes and things like that. They certainly cannot take AES. If I put encryption like AES on a pacemaker, I probably run out of battery within a year. Yeah? Yes, we can encrypt a pacemaker, but then you have to go to surgery every year. You don't want that. But on the other hand, we want to have some kind of wireless connectivity with the pacemaker. So which type of encryption do we put on a pacemaker? So we developed a new type of encryption called elliptic curve cryptography, which has the lowest power consumption per multiplication. That's how they measure it in this world. And the point here is that in order to get to so low power consumption, we have to do a very optimal design in hardware and software. Another hot topic these days is about physical unclonable functions. Physical unclonable functions is basically a way to take different chips. You know, when you manufacture a memory chip like an SRAM or DRAM or something like that, they all are a little different, just like we are. Due to the manufacturing variations, they're all a bit different. And sometimes you can find a question that will generate different responses. So it's completely unpredictable because you can't predict what the difference will be, but it can be used for authentication. So it's like a fingerprint in hardware, let's say. And there are a number of these physical unclonable functions. Again, the beauty of combining hardware and software in order to do that. And lastly, on security, what I want to mention is that we must be able to work with systems under attack. This is somehow illustrated by this picture from Heathrow, that if there is an attack going on, in the good old days, we could just take down the system. We said, oh man, there's an attack going on, someone is fiddling with my firewall, I'll take down the system for a few hours, correct it, and then I'll take it up again. Okay, that worked. Some people may be a little angry with you, but okay, you had to apologize. But that doesn't work now. The planes are flying, they have to come down. The system cannot be turned off. So how can we adapt our security and privacy policies for a system partially under attack while not taking it down? And this means that we have to learn from the attack itself. We have to learn, and here's the beauty then, using security and machine learning, actually learning from the attack and adapt our security policies according to what we understand from the attack which is going on, and then take it up again. So there is a very interesting cross path between machine learning and artificial intelligence and security. Which brings me to my last topic about distributed intelligence. So there is a lot of, also here in this conference, a lot of discussion about artificial intelligence. I sincerely think that this is one of those things that make a lot of difference and will make a lot of difference in the future, and specifically when it comes to actually having artificial intelligence agents outperforming the gold standard, which is in many cases the human expert. This was an example which was highlighted in The Economist rather recently, which I think illustrates the point. This is about detection of blindness in the retina. So if you have diabetes, there's a risk that you will become blind, that the retina will deteriorate. But if you can check for signs of this deterioration early on, this can be kind of corrected for. So that's what specialists are looking. So here you have two eyes, retinas, and one of them is at risk, the other one is not. And I guess it's rather difficult for you to judge which one is at risk. I'll give you the answer now. There you see it. The left one is at risk. And normally a human expert who would do that would, with 84% accuracy, predict which eye is at risk. And now Benjamin Graham, here from the UK, has developed an algorithm which, with 86% accuracy, predicts which eye is at risk. So the beauty here, and what's interesting with these numbers, it's that suddenly the artificial intelligence agent outperforms the human being, the human expert, the gold standard. And of course, that changes the game. Because then suddenly you may not need the experts. You can take your mobile phone, take these pictures, send it to the cloud, do this analysis, and you get it back. So it's fantastic. It will allow for much more people in developing countries to do this test, and we will be able to recognize these problems much earlier. Okay, one or two human experts may say that their job is at risk. That's true. But on the total, this is good for humanity. So we have, for sake of time, I will skip through this a little quicker. Of course, iMinds has also been doing a lot of this stuff. This is actually about learning how the heart is beating. So if you can check the difference in volume of the heart of MRI scans, and this was what you see here, that somehow tells you how well your heart is actually functioning and can be indicative of problems with the heart. So taking these pictures, it actually contains very little information, trying to understand the difference in volume contraction of the heart, and you will have a good indication of future problems when it comes to your heart. And this is what we have done. We were number 2 here out of 192 teams in this Kaggle competition. A few other things we've done on Galaxy. Here we were number 1 out of 326, and here we were number 1 out of 1,000. But the point I want to make is we are very active on this image recognition, and these people like to compete, apparently. But the point I want to make, and that's my last point, is another thing which is about how do we distribute intelligence, because all of this neural networking is done in a big cloud. So imagine, take this picture as an example. This is a kind of manufacturing site. And here you have somehow a cloud, some far away, some in a different building, let's say. And you have a number of sensors, you have maybe a few gateways, and maybe a robot. So where do I put my intelligence? Where do I put my big neural network that will learn and take decisions? Well, maybe one idea would be to put it in the cloud. That's good. The cloud has a lot of capacity. It can certainly perform the task. But what is the problem? Well, the problem is that the cloud is in many cases too slow. So to go a little further into machine learning, and probably a lot of you know this, but I'll just do that anyway, is that machine learning is built on a number of layers, and you have what we call hidden layers. And the more layers you have, the more accurate your prediction will be. So if you have some kind of handwriting which is pretty neat, this type of handwriting, maybe you just need one layer, and it will, with a large degree of accuracy, predict this is a 1, 2, 3, or 4. But if your handwriting deteriorates a bit, like my handwriting is more like this, then you need more and more layers in order to make an accurate prediction. But you don't always need so many layers, because a lot of people have rather neat handwriting. So it's only for some exceptions like myself you have to go deeper and deeper and deeper. And the trade-off here is that the more layers you have, the better accuracy you get, but the more time it takes. And sometimes you don't have the time. Again, think about the self-driving car. You have to take a decision almost instantly, so it's real time. So the trade-off here is about real-time decision-making for local nodes versus doing this analysis. And the way we solve it in iMinds is actually to split the brain. So instead of putting the full neural network in the cloud, we have developed a platform to actually distribute virtually any type of neural network across a number of nodes. You can put part of the neural network on the gateway, part of it on a sensor node, part of it on the robot, for example. And this will allow us to do what we needed to do, have all the intelligence needed because you have a big neural network, but you can take decisions locally in real time. And that's our Diane platform, which is a very interesting topic in itself. But for sake of time, I think I'll stop there. I wanted to talk about 3 aspects of Internet of Things and the learning Internet of Things, about how we connect things, how we establish trust in between all these entities, and how we distribute the intelligence. And I want to leave you with one word of thinking. I started with this robotic police and the self-confined. When we allow these systems to solve solutions, let's not think self-confined. Let's think distributed. Let's not think around how we would solve it. We need to think differently. And I want to leave you with this quote by Edgar Dijkstra. He's a very, very famous mathematician and data scientist. He's not with us anymore, I'm afraid. But he said that the question whether machines can think is about as relevant as the question of whether submarines can swim. It really doesn't matter. The submarines are very good at transporting people from A to B underwater. Are they swimming? That's irrelevant. They solve the problem. And I think we need to think the same when it comes to Internet of Things, and we need to start thinking distributed. Thank you so much. It was a pleasure. Hope you enjoyed it.